Green chemistry, integration of photophysical and photochemical green reactivities. In this lesson, we will build an intuitive picture of light-driven chemistry, connect it to clear mechanisms, and quantify it with simple math, statistics, and clean graphs. We start with two ideas. First, photophysics, what happens to molecules after absorbing light, such as energy levels, excited states, and emission. Second, photochemistry, using that excited energy to make and break bonds. The green goal is to do useful synthesis with fewer hazards, lower energy, milder conditions, and superior selectivity. Here is the Jablonski diagram. We show singlet ground state, excited singlet, and excited triplet. From the excited singlet, we can fluoresce, cross to triplet by intersystem crossing, or emit from triplet as phosphorescence. Critically, we can also funnel that excited energy into chemistry. Let us map a simple green photoredox cycle. 1. The photocatalyst absorbs light to reach an excited state. 2. The excited photocatalyst exchanges an electron with the substrate, creating radical ions and driving the key step. 3. The substrate fragment evolves into product, and the catalyst is regenerated, closing the cycle. We quantify excited state behavior with simple rate constants. The total decay rate K total equals the sum of radiative Kf, non-radiative Knr, and reactive K reaction. The lifetime, tau equals 1 over K total. The fluorescence quantum yield phi, F equals Kf over K total. The product quantum yield phi, P equals K reaction over K total. These simple ratios guide design. Increase the channel you want, decrease the others. Statistically, dynamic quenching follows the Stern-Volmer relationship. I naught over I equals 1 plus K SV times the quencher concentration. A straight line fit gives the slope K SV, which equals the quenching rate constant times the natural lifetime. This is a fast way to quantify how strongly a quencher diverts excited states away from reaction. Graphically, light can open a lower barrier pathway through an excited state surface. The thermal path has a high activation energy, while the photopath lowers the barrier, enabling milder, greener conditions. Quantitatively, green chemistry tracks efficiency. Atom economy equals mass of desired product over total mass of reactants times 100%. E factor equals mass of waste over mass of product. Lower is greener. We also track energy input per mole. Visible LEDs can drastically reduce energy use versus hot thermal routes. Design checklist for integrating photophysical and photochemical green reactivity. 1. Choose wavelength to match the catalyst absorption for efficient excitation. 2. Tune solvent and oxygen content to favor the productive pathway. 3. Maximize the desired rate constant relative to all other decay channels. 4. Validate with Stern-Volmer analysis and quantum yield measurements. 5. Report atom economy, E factor, and energy use per mole for transparent green metrics. Summary: photophysics tells us how molecules handle light, excitation, and decay. Photochemistry turns that energy into bonds, guided by rates, yields, and selectivity. Green chemistry integrates both to deliver cleaner, safer, and energy-efficient synthesis, verified by quantitative metrics and clear graphs.